Welcome to the second video on a complete course in General Relativity. This series of videos will guide you through the fundamentals of General Relativity, starting from the basics and building up to more advanced concepts. Whether you are new to the subject or refreshing your knowledge, this course will provide you a step-by-step approach to mastering General Relativity. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the second video on learning General Relativity. Before I go ahead and start with today's video, I need to apologize for a small error which I made in the last video, and here is a small correction. And also I would like to all the subscribers who have watched my video in details and have really pointed out what was the error. Now I have mentioned the date of birth of Pierre Gassendi to be something which is not right, and the right date would be 1592 to 1655. So this was the error that I made, not intentionally, in my first video. Thank you subscribers for pointing me out, and this is the correct date of birth and date of death. So as far as the first video was concerned, we start with today's lesson with what is called a change of coordinates between frames. I mean to say, this would be frames of references, and let us look how the change of coordinates helps us in a better understanding of relativity. Now this is basically the screenshot of the earlier video where we were talking about the Galileo and the laws of motion, how the stone falls, whether it falls backwards or forward. So the possibility of using the laws of physics in different frames of references actually arises from the fundamental principle, which is this: the laws of physics must hold true in all inertial frames of reference. Well, this is a key idea in classical mechanics, particularly in the study of relative motion and transformation of coordinates between reference frames. Now, this transformation of coordinates between reference frames is crucial in classical mechanics due to certain reasons, and these reasons are very pertinent in our understanding. The first, in what is called relative motion or relative velocity, it helps describe how two observers in different frames perceive the motion of an object. The second is called the invariance of the laws of physics. So in classical mechanics, the fundamental laws are invariant under Galilean transformations, which means that the same physical laws apply in both the boat frame and the shore frame, which is on the right hand side on the left corner of your screen. And also it leads to velocity addition, which we will look that the Galilean transformation also leads to the classical rule for adding velocities. So the concept of changing reference frames and transforming coordinates between them sets the stage for more advanced theories like special relativity, where these transformations are modified to account for high-speed motion like the speed of light, which leads to Lorentz transformations. Now, in order to look this into a much more constructive and mathematical way, I would like to show you this one. Let us consider two different frames of reference, S and S prime, which I can say, you can say that the relative motion or the relative movement is kind of a translation. That means the relative orientation of the Cartesian axis do not change as time flows by. And this has got a constant velocity, which is v. So for simplicity, the frames of reference, again S and S prime, will be chosen in such a way that their axes are coincident at t equals to 0. Here it is. So I again repeat that for simplicity, the frames of references S and S prime will be chosen in such a way that their axes are coincident at t equal to 0, and their x and x prime axes have the direction of the relative movement. Now, at an arbitrary time, say for example, if I take add t, the distance between the coordinate origins, which is this one, O and O prime, is d O prime equals to v times t. So the transformation of the Cartesian coordinate, now which I would like to show you, x at a point P, can be further illustrated in this type of a diagram. So what I have done is that, as you see, that I have taken this DOP, which is just the summation of DOO prime and DO prime P. And this can be written simply as this, summation of 2. So together with the relation between distance and Cartesian coordinates, we can say that DOP is not equal. This is equivalent to x, and DO prime P would be equal to x prime. This by mistake I have written as p prime, but this should be DO prime P, which is equal to x prime. I would say equivalent to x prime. So from here, if we go to the next page, we can say that x equals to Vt plus x prime. Now this equation, as we see that although the coordinates transform, this seems to us completely evident and natural. Why? Because it should be emphasized that the result that you see right now, x equal to Vt plus x prime, is closely linked to the invariant character which is given to distances in classical physics. That means in principle we can say that this equation DOOP equals to DO prime, which is equal plus DO prime P. I'm thankful that I've got these things right. This is only prevalent and has only a meaning when all the distances are measured in the same frame. And what do I mean by the same frame? The S and the S prime. So and this is again, I'm showing the picture on the left hand side so that things become easier to understand. But coordinate x is the distance DO pre as measured in S frame of reference, whereas x prime is the distance measured in DO prime P, which is measured in S prime difference. From this, what we can say is that if we read DOP and this equation is read in frame S, then DOP can be replaced by x. So if this equation is read in the frame S, then DOP can be replaced by x. But we should remember that DO prime P should not be substituted by x prime. This is not possible. So, however, owing to the invariant character ascribed to distance, it becomes correct to replace this part, that is, x prime is the value of DO prime P measured in S prime is replaced by the coordinate x prime of the point P. So this actually shows that how the coordinate transformation happens and which coordinate can be replaced by this and which cannot be replaced by this. So this again we take the same equation. This one, the coordinate transformation of this equation would not be consistent unless there is a fundamental assumption that was accepted. And what is that assumption? It is called the invariant time. So time is not changing, invariant time. So in fact, if the time needed for the displacement of DOO prime was, for example, t prime when measured in S prime frame of reference, then this equation, as you have seen earlier, regarded from which can be regarded from S prime, would lead to this new equation Vt prime plus x prime. Now as a result, this result is compatible with this equation, the earlier one, Vt plus x prime, where there is no prime on the t part. So the result is compatible with this. Yes, there is a condition only if t prime equals to t. So therefore both assumptions, so this is why valid. So I can say that the both assumptions about the nature of space and time, we can say that the distances and times are invariant and they are strongly intertwined and they are mutually very much necessary. So the time intervals, distances and time intervals remain unchanged and these are deeply interconnected with mutual dependence. So this is pretty important. Now, although the classical conjectures about the nature of distances and time seem to be unquestionably confirmed because of our daily experiences, however, few things become very important. Number one is the classical assumptions confirmed by daily experience. What do I mean by that? The traditional ideas and distances and time as understood in classical mechanics appear to be fully supported by everyday observations. However, everyday experience involves only a limited range of relative velocities. Obviously, we mean that things which are moving much slower than the speed of light. And there is a caution in generalization, because while these assumptions work for everyday situations, they may not apply universally, especially at high velocities. And it is more accurate to say that classical assumptions about space and time are appropriate for low velocity scenarios but may not hold for high speed cases where relativistic effects become significant. All this actually leads to this idea that classical assumptions about distances and time are confirmed by everyday experiences at higher velocities, such as those approaching the speed of light. This assumption may not hold right, and relativistic effects should be considered. So from here, what I can show you again is this. If you have not looked into the earlier video, please look into this. This was the earlier video where I showed you the coordinates. So here the coordinates y and z are the distances between the point P and two coordinate planes which are mutually orthogonal on the x-axis. Remember, they are mutually orthogonal in the x-axis as given by in the previous video. However, in this kind of a moving frame of reference which I showed you, the frames S and S prime are not orthogonal, but they are equally oriented, and their X and X prime axes are basically superimposed on each other. So for those coordinate planes which are shared by S and S prime, these coordinate planes are shared by S and S prime. This property together, I can say, with the invariance of the distance, imply that the coordinates y and z from the earlier figure are the same in both frames of reference, obviously. So in sum, the Cartesian coordinates of a given at a point instant t, if I take a time as t, can be transformed as this: x prime equals to x minus vt, y prime equals to y, and z prime equals to z. And you can already understand from this, this is known what is called Galilean transformations, which is honored after the name of Galileo Galilei, the famous mathematician, astronomer and physicist. Now we will take up now the importance of Galilean transformation in terms of understanding relativity, and then we will look into the mathematics, but this is truly important. So if I consider Galileo di Vincenzo Bonatti di Galileo, born in 1564, this transformation led to, number one, the foundations of classical mechanics, because it provides the framework for describing motion and interaction between objects. Number two, obviously introduces first the concept of relative motion, demonstrates that motion is relative to chosen frame of reference. Third, it is that it is first provided a key transition to relativity, because it highlights the need for a new framework when dealing with high-speed motion, making it crucial for the evolution of modern physics, and obviously these are applicable for low velocities. So in summary, we can say that Galilean transformation is a very, very fundamental tool in classical mechanics that empowers the connection between the observations of motion in different frames, and it lays the groundwork for understanding relativity, obviously through its limitation, which are lower than the speed of light. Now all these equations that we see, the three equations on the left hand side corner that you can see, can be joined into one vector equation which uses the position vector of the point P, R as x, y and z. And because this can be further written as this one, and this is a vector equation, this is vectorial in nature, I would say the nature is vector. It is even valid when the direction of v, velocity, does not coincide with x or x prime axis. So in fact we can say that the vector relations, this is very important, are not at all affected by rotation of Cartesian axis, and that gives us a nice tool for calculations. So the transformation are complete with the invariance of time. That means this equation are complete with t prime equals to t. I am to say, yeah, so this would be equal to this. Now, the next aim, what we are trying to understand from this Galilean transformation is that given this equation, can we find out what is called the Galilean addition theorem of velocities? Now, hold on. I will just try to explain you in very simple word. What do I mean by this? So it actually means that to describe how the velocity of an object changes when observed from two different reference frames that are moving relative to each other, but at a constant velocity, obviously, because this is classical physics and Galilean transformation deals with constant velocity. So first of all, we will go through the step of calculation very easily. So we denote r is the position vector in the moving frame of reference, r prime. R is the position vector in the stationary frame of reference. V is the relative velocity between the two frames constant, and r is time equal in both frames in classical mechanics. So the relation between the position vectors in two frames of reference, if you're trying to equate this particular equation, so to find the velocity transformation, we first would differentiate both sides of the equation with respect to time t. Obviously, since in Galilean transformation t equals to t prime, time is same in both frames of reference, we can simply differentiate with respect to time t. So when we, the derivative of r with respect to t gives the stationary frame u equals to dr by dt, and in the moving frame of reference it gives u prime equals to dr prime by dt. It represents the velocity in the moving frame, and v is basically the constant velocity of the moving frame to the stationary frame. Now in further differentiating, when we differentiate both these times with respect to time t, so what we get is this one. Very simple. What we get is this one. And here, you know, dr by dt is already equal to u. We know that. And this one is equal to v. So if you want to write this equation in a simple way, so we can say dvt by dt equals to v. And substituting the values, we get u prime equals to u, the green arrow which is showing, and it equals to v. So what becomes important is that we can write it in this vector format, and what it shows that the velocity in the moving frame of reference, which is u prime, equals to the velocity in the stationary frame of reference, which is u, and minus the relative velocity v. So this is, I would say, actually shows how the transformation and the mathematics actually happens. Now again, I would like to refer to my first video where I have actually shown, I have written refer to the first video. So here you can see the value between the simultaneous positions of P and Q is not modified by Galilean transformation. I mean to say, this invariance cannot surprise you because it has already been assumed in the building of the coordinate transformation. So the value of the distance between simultaneous position P and Q marked in red circle is not modified by Galilean transformations. What do I mean by this? First is that the principle states that the distance between 2 points remains obviously the same, even when observed from different inertial frames that are moving relative to each other. So in other words, you can say, if you measure the distance between 2 points from one moving frame and then measure it again from another moving frame, you will get the same result. The second thing is that these are mathematical transformations, and the coordinates of points in one inertial frame to the coordinates of the same point in other frames is moving constant. So the Galilean transformations are actually built upon the assumption of distance invariance. So that is why, and this, so because they remain the same, because Galilean transformation are built upon the assumption of distance variance, so I can say it is not surprising, because the concept of distance invariance is fundamental principle of classical mechanics, and the Galilean transformation is derived from that. So right at the beginning, what I tried to tell you is that the distance between simultaneous points of P and Q is not modified by Galilean transformation, and this invariance cannot surprise you, and this is the reason that it doesn't surprise you. So in a sense, we can say that the Galilean transformation are consistent with the idea of the distance between 2 points in an absolute quantity that does not change to the relative motion of different frames of references. So from here, what we can actually come is that we are actually using this part So this is basically how the positions and velocities are actually happening between two frames of reference. But what actually it is occurring on, what it is acting on, these are actually the motion of bodies. So on the left hand side we have got frames of references. On the right hand side we have got oscillating pendulum, which are motion of bodies, and the key linking factor between them is what is called the relative nature of motion. And Galilean transformation demonstrate that the laws of motion, including this motion of bodies, are valid in all inertial frames of reference, and this leads us to what is called the principle of inertia. So the Galilean transformation demonstrates or shows that the laws of motions, including the principle of inertia, are valid in all frames of reference. So here is a summary which you can pause and read, that the principle of inertia is inherently preserved under Galilean transformation because this transformation involves a shift between two inertial reference frames at constant velocity relative to one another. So you can see that how these are interlinked. The moving of the object and the motion of bodies actually leads to what is called the principle of inertia. And that is what we are going to take up into the next part of our video. Clean and clear understanding of principle inertia and how it shows the path towards learning relativity. Now, as per Galileo Galilei is concerned, Galileo's insights were basically identified the tendency of objects to persist in their state of motion, and that is basically the key feature of movement. However, Isaac Newton in his famous Principia Mathematica laid out that every body preserves in its state of rest of uniform motion in straight line unless compelled to change by a force impressed thereon, which actually leads to what is called the Newton's first law of motion. But now you can see that how from Galileo's understanding, philosophical or mathematical, Newton's first law actually came in, and how the relativistic stage is slowly being set in to understand this. Now, there are certain experimental challenges which we encounter, that a body's movement cannot be consistently classified as rectilinear and uniform across the reference systems. However, if a body has a constant velocity in one reference frame, obviously it will maintain rectilinear and uniform motion in another system, translating at constant velocity relative to the first. So if the principle of inertia is valid in one frame of reference, obviously it will be valid in a family of reference systems. And this family is identified by what is called an absolute space. So Newton actually proposed that the principle of inertia is valid in reference of systems at absolute rest and any other system translating with constant velocity relative to his absolute space. And these reference systems are actually termed as inertial frames, privileged due to their consistent motion in absolute space. So what is important is that what we find is that Newton emphasized using relative spaces and motions in practical affairs. So absolute positions and motion are often abstracted to consider underlying physical realities. Also, you will see that in practice, inertial frames are recognized not by their motion relative to absolute space, but by their adherence to the principle of inertia. So there is a challenge in verifying the principle of inertia without having a body free from forces to conduct their verification. So we can say that inertial frames are defined as those reference systems where the principle of inertia and the fundamental laws of physics hold to a satisfactory degree despite the complication or in verification. So that is what is important, that the inertial frames are defined as those reference systems where the principle of inertia and the fundamental laws of physics hold despite the complications in verification. So from this part of the video we get certain very important, I would say, concept. First is the persistence of motion, which is central to the concept of inertia. Next is Newton's first law of motion, which we will look a little bit deeper into the next part of the video, formalization of inertia as a fundamental principle, and the challenges in definition, because difficulties in identifying forces acting on bodies and establishing uniform across reference frame systems. Absolute phase, theoretical framework that underpins the concept of inertial frames, and the need for a force-free body complicates the validation of inertial frames. So we would like to take a pause in today's video where we have completed the principle of inertia, the Galilean transformation, and the mathematics involved showing the Galilean transformation, how it happens. So thank you very much for watching today's video. If you have liked the video, do not forget to subscribe to my channel and click on the bell icon to get all the notification from Physics for Students. This is my email ID which you can write, and you can subscribe to my other channel, General Relativity Explained. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. So this is the second video in the course of learning general relativity. Physics for Students will continue with this course and the other courses and the other areas of physics and mathematics which I generally do, and I do make videos to make physics and mathematics more interesting and fun-loving. We'll soon meet you, but till then, may the good Lord be with you.